Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of today's lecture is Liquid Solid Fluidization by Power Law Liquids. We will have a comparison of a packed bed when the flow is downward and upward, then we enter into the fluidized bed conditions. In the downward flow through packed beds of particles, no relative movement occurs between the particles except in the case of a unstable initial packing. If the initial packing is not properly stable, have not been properly vibrated and shaken before the packing, then that means the initial packing is unstable. So, under such conditions there will not be any relative movement of the particles if the flow is downward. When there is no relative movement of particles, what does it mean? It means that the particle is stable. It is like a fixed bed, it is like a packed bed. So, for the packed beds we have seen frictional pressure drop equations both under the streamline conditions as well as the turbulent conditions. So, what we understand from there, for Newtonian fluids delta P is directly proportional to Q volumetric flow rate, but for shear thinning fluids delta P is proportional to the Q to the power of less than 1. This you can get whatever the frictional pressure drop equation that we got, F is equals to some alpha constant by Re prime or Re star plus beta constant. So, that you expand and then you write in terms of pressure drop versus volumetric flow rate. Then what you can understand, pressure drop is proportional to the Q to the power of less than 1 if it is a shear thinning fluid. If it is a shear thickening fluid, pressure drop is proportional to the Q to the power of greater than 1. This you can understand from the frictional pressure drop equation whatever we have derived in previous 2 lectures for the case of packed beds, right. So, directly those equations are not in terms of volumetric flow rate, but they are in terms of a superficial velocity. So, both of them are similar because superficial velocity, if you multiply by the cross section area of the bed through which the fluid is flowing, then you get the volumetric flow rate. Okay. So, from those equations this is what you understand, right. But if the flow is under turbulent region, then we understood that delta P is proportional to the Q to the power of 1.8 to 2 irrespective of the nature of the fluid, that is whether Newtonian fluid or shear thinning fluid or shear thickening fluid. That indicates under turbulent conditions the non-Newtonian effect is very less in the case of packed beds, especially when the flow is downward and then there is no relative movement between the particles. Now, what happens? Upward flow through beds of particles takes place. Okay. So, that is what we are going to see now. So, this is what pictorially we see now. So, what we have here? We have a column, right. At the bottom there is a perforated plate and then particles have been poured to some extent to some portion of the column onto this perforated plate, right. So, the perforated plate perforation is such a way that it is the perforation is size of the perforation is smaller than the particle size, so that the particle should not fall down or fall down through the perforation of the plate. Why the perforation is required? Because we have to allow a fluid to enter for the required momentum, heat or mass transfer or reaction whatever is occurring, right, for this reason. So, now these different pictures are shown here, have been shown here. So, this is with increasing the velocity, right. So, now the top of the packing is not covered or constrained by another perforated plate. Okay. So, what happens if the velocity, whether you use gas or liquid, if the velocity is very small, or if the velocity is small so that there is no relative movement of the particles, right, there is no relative movement of the particles, or the entering fluid is not having such a high velocity or such a force that it is altering the bed arrangement. It is not making any rearrangement of the bed, such a way the velocity is there. So, then whether it is downward flow, upward flow, we can say that the bed is under fixed conditions. There is no relative movement of the particles, the velocity is maintained such a way. remember. So, whatever that we are going to discuss in this lecture is primarily confined to liquid solid fluidization only, right. Why? Because to some extent whether the fluidizing medium is liquid or solid, the behavior is same, but after certain value of the velocity, fluidizing medium velocity, the behavior changes, the fluidization behavior changes, if it is a solid, if it is a gas, gas solid fluidized bed. So, but we are not going into the gas solid fluidized beds, that is not required for us, because we are talking about the liquid solid fluidization, especially the liquid is a power law fluid or Bingham plastic fluid or such kind of non-Newtonian fluids. Okay. Now, next what happens, this is the case at low velocities. If gradually if you increase the velocity, still it is whether it is gas or liquid does not makes difference in the second picture also. The when you gradually increase the velocity of the fluidizing medium, then what happens, the drag force on the particles is balanced by the buoyant weight of the particles, or the drag acting on the particle is balanced by the buoyant weight of the particles, and then once this point reaches in terms of the velocity, because we are increasing the velocity, that means you are increasing the force of the fluid that is entering into the bed, right. So, then from that point onwards, the rearrangement of the particles will start take place. Rearrangement of particles will start take place, and then particles would be slightly rearranging from one point to the others, and then initially they are compact, initially they are lying onto each other, there is a stiff contact because of low velocities that is not being moved. So, as the velocity increases slightly, there is a rearrangement of the particles, slight rearrangement like this, changes slightly their locations, right. That occurs when the velocity is such a way that the drag is balanced by the buoyant weight of the particles. Whatever the drag on the particles are there is balanced by the buoyant weight of those particles. So, then that is a slight rearrangement takes place. If you further increase gradually, keep on increasing the velocity, what happens, the the particles, more and particles becomes looser, and then they move away from each other, right. So, now what happens, the same number of particles are occupying more space in the column, they are occupying more space in the column. So, then that means what happens, the voidage is increasing, voidage is increasing. So, if the voidage is increasing, what happens, the resistance to the flow decreases, right. So, then like this there would be a point of velocity at which is known as the minimum fluidization velocity, at which where this pressure drop is balanced by the buoyant weight of the particle. So, that point of velocity at that conditions we call it bed is started fluidizing under fluidized conditions. If you further increase the velocity, the bed become looser, and then particles move at higher distance from each other, the gap between the particles increases and then voidage increases, right. So, like that the bed keep on expands, and then after this point of minimum fluidized conditions what will be there, the behavior of the bed is going to be different depending on the nature of the fluidizing medium. If it is liquid, we have almost like a homogeneous particulate fluidization will have. What does mean by homogeneous particulate fluidization? That means at any cross section, if you measure the voidage, you are going to get approximately the same voidage, right. But if it is not homogeneous fluidized bed, then what happens, at one location the voidage is different, its other location it may be different, like that voidage is going to be very different from one point to the other point. Even in this case also particulate fluidization also, particulate homogeneous fluidized bed also, there may be slight variations voidage, you do not get exactly, let us say at this location it is 0.4, so exactly 0.4 you get the other location, slight variation 0.39, 0.41 like that on the average, if you take on the average at any cross section, you get the same voidage, approximately the same voidage. Okay. That is what such kind of fluidized bed you get if you have a liquid fluidized bed, right. So, but if you have a gas fluidized bed, then bubbling fluidization, fast fluidization, all those different kind of behavior are possible, that we are not going into the details, because that is not the theme of the lecture. We are taking only liquid solid fluidization, right. So, now, but after this particulate fluidization condition also reached, so you can see almost like bed is expanded to the almost to the top of the column, right. So, the velocity is so high that the bed is expanding, fluidizing, and then it is almost like the reached particles are reached almost top of the column, right. Further, if you increase the velocity, then there would be a condition where pneumatic fluidization takes place, where the particles may be particles are being thrown out of the column, and then they are collected back by using a cyclone separator at the top, and then sent back to the bed from the bottom again. That is all different things. So now at such high velocities, the particles are very far from each other, and then such conditions we call them pneumatic fluidization. So, pneumatic fluidization behavior is also approximately same for the gas or liquid fluidizing medium. Okay. So, pictorially this is how you can say how the fluidization of the particle behavior look like with increasing the velocity. This is what we can understand. So, now we see the same details again here. So, upward flow through beds of particles, the frictional pressure drop should be same as of the downward flow case if under two conditions. One is if the bed is constrained at the top also by a closing perforated plate, or the velocity is low such a way that the rearrangement of particle is not taking place, or there will not be any relative movement of the particles if the bed is not constrained at the top. These two conditions, under two conditions we have whether upward flow or downward flow, the frictional pressure drop is going to be same. Okay. Then by gradually increasing the flow rate, point at which drag on particles becomes equal to their buoyant weight, particles rearrangement should occur within the bed as I shown pictorially, and then expands in order to offer less resistance to flow, because the rearrangement is taking place. Now, particles are having more space to occupy, so they are slightly away from each other. So, then obviously the voidage is going to be higher than the initial voidage. So, if the voidage is higher, so then it will be offering the less resistance. By further increasing the flow rate, what happened? Bed gradually becomes loose and reaches a point where the particles are separated from each other, and then particles become freely suspended in liquid stream, and bed is said to be under fluidized conditions. So, the particles, even if they are solid particles, they behave like a fluid particles, they are under fluidized condition, right. So, that is the reason these kind of beds are called as a fluidized beds. Even the solid particles behaves like a fluids, they are suspended like the fluid particles. Okay. By further increasing the flow rate, particles move further apart and then increase bed of voidage, but the pressure drop remains constant. Pressure drop almost remains constant, because after reaching certain minimum fluidization conditions, whatever the velocity increase, bed voidage increases, but the pressure drop does not change. Pressure drop does not change. Okay. So, the change in pressure drop, whatever is there with increasing the pressure drop with increasing the flow rate or superficial velocity is there, that is there only for the case of a fixed bed, or the conditions such a way that there is no relative movement of the particles, even if it is not fixed bed, if it is not constrained at the top. But after that fluidization start occurring, if you gradually increasing the flow rate, what happens? The voidage increases, but the pressure drop remains constant, because from that point onwards the drag force is balanced by the buoyant weight of the particle, or the drag force is balanced by the buoyant force of the particles, right. So, then from that point onwards, obviously the pressure drop is going to remain constant, and it is approximately equal to the buoyant weight per unit area of the bed. till this point system behaves in a similar manner whether the fluidizing medium is gas or liquid. So, that till that point where the pressure drop start becoming constants. So, that point we call as a minimum fluidized conditions. The point at which the pressure drop start becoming constant even if you increasing the velocity volumetric flow rate. So, that point we call it as a point of incipient fluidization, right. So, that incipient fluidization or the fluidization starts taking place. Till that point whether the fluid is gas or liquid, the same equations are going to be used in order to get the frictional pressure drop. Okay. So, that means the gas or liquid does not make any difference. Okay. Liquid fluidized bed continue to expand in a uniform manner with the degree of agitation of particles increasing progressively, and this is said to be under particulate fluidized conditions where the average voidage at any cross section of the bed if you take, it is going to be approximately the same. Then such fluidized beds we call particulate fluidized beds. And then qualitatively similar behavior for a non-Newtonian liquids also possible. Like if your fluidizing medium is non-Newtonian liquid, then obviously then also you are going to get the similar behavior, qualitatively similar behavior you may be getting, right. Now, in terms of pressure drop versus volumetric flow rate or pressure drop versus superficial velocity, if you see the liquid solid fluidization behavior, how does it look like? Right. So, then obviously it has to be upward flow, because upward flow only then it is possible that the fluidization of the particle is taking place, right. So, now you take a column and then you have a perforation at the bed at the bottom of the column, then you pour in some particles, okay, crushed glass or whatever the packing material you use, and then you do not constrain at the top. You do not use any other perforated plate at the top for the constraining this bed. Then what you do? You allow some fluid to flow through it, especially liquids you take, because we are talking about the liquid solid fluidized beds, right. Then for a given average volumetric flow rate or superficial velocity, what is the corresponding pressure drop that you measure? Experimentally that you measure, and then that whatever the delta p versus V naught information is there, that you plot on a log coordinates, Then how do you what kind of cost you expect is this one. So, initially when the velocity is low, when gradually velocity is increasing, the pressure drop increases. Because till this point A, what happens, the velocity is such a low that it is not causing any rearrangement of the bed. And then there is no relative movement between the particles, even it is not constrained at the top. But if you further increase the velocity, what happens? The slope of this curve gradually diminishes and then reaches a point B at which the pressure drop is maximum, right. Okay. Then further if you increase the velocity, then what happens? This pressure drop slightly decreases. From A to B there is an increase in pressure drop, but there is a slight increase. From B to C there is a decrease in pressure drop with increasing the velocity, right. So, but that decrease is also very small, right. After this point, whatever the value you go to the whatever the higher superficial velocity you take, the pressure drop is not going to be changing, because from this point onwards whatever the pressure drop is there, that is balanced by the buoyant weight of the bed. Okay. So, that is the reason. So, from that point onwards the pressure drop is going to be constant. Initially you increase the superficial velocity and then you reach this, trace this ABCD curve. Okay. Right. Now, after reaching D, because after that point you realize that whatever increasing the after this C point, after this point what you realize that whatever the increase in the fluidized medium velocity, pressure drop is not changing because of the balanced pressure drop and then buoyant weight of the beds, right. So, then what you try to do, you try to decrease the velocity gradually, you decrease gradually velocity. Okay. Then what happens? To certain point C, you are going to get back your curve, CD curve. Now you will be getting DC curve, you are decreasing the velocity. Then further decreasing the velocity, what happens? You are not going to get the pressure drop same as pressure drop at B and then A, but rather what happens, further decreasing the velocity, the pressure drop still remains constant up to the point E, up to the point E. Why it is? Because initially the when you do the initial packing, the bed was compact, right. So, it was giving slightly higher pressure drop at this corresponding velocity, right. But when once it has been fluidized and then you are gradually decreasing the velocity, what happens? The particles initially at the at the D point, they are fluidized conditions of free from each other, they are suspended like fluid particles, right. As decreasing the velocity, particles the still up to C point, still they are free from each other, and then they are suspended like a fluid particles like under fluidized conditions. But further decreasing the velocity, what happens? The particles start settling, and then distance between these particle decreases, and then there would be a point E at which the particles are lying onto each other. They are just lying onto each other, but there is no vibration or mechanical agitation kind of thing. Additional external force is not there, so that this particle become compact. Since it is initially fluidized, the bed is initially disturbed, then again by decreasing the velocity, the particles are settled down and then resting onto each other. So, then at that conditions, voidage would be the slightly higher than the initial packing voidage. That is the reason the pressure drop is going to be slightly less up to this E point. Now, after this E point, further if you decreasing the velocity, what happens? The pressure drop gradually decreases, because now after this reaching this E point, when you decreasing the velocity, the particles are at this E point, what happens? Particles are already resting onto each other. They are like confined, they are now like a packed bed, fixed bed kind of thing. Only thing that the slight the packing is not very compact as initial packing, because they are disturbed, the packing is disturbed, and then they are just resting onto each other. So, further decreasing the velocity, there would be no compacting of the bed will not take place. So, then what happens? The voidage is going to remain constant, but what happens? The pressure drop is going to decrease, and then you are not going to get this, let us say origin O to A curve, whatever is there, that you are not going to get. You are going to get E F curve, and then the pressure drop at smaller velocity is slightly lesser than the pressure drop while increasing the velocity. Why? Because while decreasing the velocity, the bed rearrangement has been taken substantially, and then even when you decrease the velocity to almost very small close to zero velocity, the voidage is slightly higher than the initial packing voidage. That is the reason the pressure drop curve, your OA curve whatever is there, that is not being traced, rather you get EF curve. So, this point E whatever is there, we call fluidizing point, or a point of incipient fluidization, okay. And then corresponding velocity is whatever is there, minimum fluidization velocity, that is what we call. So, now we have to find out how to find out this minimum fluidization velocity, because in the fluidized bed conditions, we know that the pressure drop is constant, right. So, now this bed is, we can divide into two parts. Up to this point E, whatever is there, that behavior is same like a fixed bed conditions. So, then whatever the equations that we have developed in the previous lectures, those things we can use, but after that point the bed is under fluidized conditions. So, here in these conditions we understand this pressure drop is constant, and it is approximately equals to the buoyant weight of the bed. So, that we can calculate if you know the minimum fluidization. So, how to find out this minimum fluidization, that is what we are going to see, and then we are also going to see how to find out the friction factors etc. for this minimum fluidized conditions. So, whatever the details that we have discussed here in this figure, the same thing is presented here in the text form as a notes, the curve between pressure gradient and superficial velocity when you plot on log coordinates for a bed which is not constrained at the top, and then flow is taking from from bottom to top as a upward motion, then a linear relation can be obtained up to point A where the bed is fluidized and where expansion of the bed starts to occur. Till that point there is no expansion start, but from A point onwards it start to occur. Then the slope of curve gradually diminishes as the bed expands. As liquid velocity is gradually increased, the pressure drop passes through maximum value at point B, then falls slightly up to point C, and then eventually attains a nearly constant value independent of the liquid velocity, and follows CD line. Then if velocity of liquid is reduced again, bed contracts until it reaches the condition where the particles are just resting in contact with another up to point E. At point E, it has the maximum stable voidage for a fixed bed conditions. This voidage whatever is there, that is maximum for a fixed bed condition, and then minimum for a fluidized bed condition. Okay. Further, if you increase the velocity, you can increase the voidage, right. But this voidage at the point E whatever is there, that is the maximum for the fixed bed and then minimum for the fluidized bed, right. The corresponding velocity is also minimum fluidization velocity. Below that velocity there will not be any fluidization. That is the reason this voidage whatever is there, that is epsilon mf is written, which is the minimum voidage for the fluidized conditions and then maximum voidage for the fixed bed conditions, and then corresponding velocity whatever is there, we call it minimum fluidization velocity. Up to this point E, no further changes in the voidage of the bed occurs as the velocity is reduced, provided it is not shaken or vibrated. Then pressure drop EF in this reformed packed bed may be less than that in the original bed at the same velocity because of the rearrangement of the bed. If the liquid velocity increased again, new curve EF would normally be retraced and slope suddenly drops to 0 at fluidizing point E. So, in the figure we have increasing the velocity, so then O, A, B, C, D curve, that is what we have, while decreasing the velocity we have D, C, E, F curve that we are having. So, now again if you increase the velocity to see how the fluidization will take place. So, then under such conditions we are going to get this E, F and then C, D curve rather than O, A, B, C, D curve. Okay. So, once the bed is disturbed, you are not going to get the same OA, ABCD curve, whatever the figure, that log of pressure drop versus log of fluidization velocity that we have drawn. Okay. Once bed is disturbed, you are not going to get the same OA curve again. Okay. You are going to get EF curve only. In an idealized fluidized bed, pressure drop corresponding to ECD line is equal to the buoyant weight of the bed per unit area, but in praxis obviously in reality small deviations from this value may be observed due to several reasons like channeling, interlocking of the particles, wall effects, etc. Point B is situated above the CD because frictional frictional forces between the particles must be overcome before the rearrangement of particles can occur. So, one example, we take a CMC solution 0.9 and then it is passed through a bed of 3.57 mm glass piers, and then packing has been done in 100 mm diameter column. Then the experiments have been carried out, whatever the minus delta P versus V naught information is there, that has been plotted on a log scale. So, that now you can see the points are slightly scattered, right. But what you can see here, you can see whatever the details that we have seen in the theoretical thing that we are getting back here. While decreasing this, there is a slight change here. So, the dotted one is increasing one, the solid one is decreasing the velocity. So, even not only the nature of the curve, even that whatever A, B, C, D and then D, E, F curve are there. So, that also we can clearly see here. So, velocity corresponding to incipient fluidization point can be calculated by equating the pressure drop across the bed to its buoyant weight per unit area. So, voidage at the onset of fluidation should be correspond to the maximum value attainable in the fixed bed, but minimum value in the case of a fluidized bed. Thus, fluidized bed's total frictional force in particles must be equal to the buoyant weight of the bed. So, let us say frictional force whatever is there. So, minus delta P multiplied by, say, let us say cross section area is S naught, then the volume of the fluid that has been replaced is rho s minus rho, right. If you wanted to know the mass of the fluid that has been replaced by the particle movement, so it has to be multiplied by the volume of the bed, so L S naught. But in the case of packed bed, what we have only 1 minus epsilon fraction of the solid particles, not the entire column is filled by the particles. So, void space is epsilon is there. So, 1 minus epsilon is the fraction of the particles that are present, and then so this gives the mass of the particles, right, and then multiplied by g. So, that gives this entire expression will give you the band force of the bed, of the entire bed. Okay. We are not talking about one particle for the entire bed, because we are multiplying by this 1 minus epsilon, right. So, now this S naught is cancelled out. So, minus delta P is rho s minus rho 1 minus epsilon L g, that is what we get, right. So, this is the constant pressure drop in the case of fluidized bed. That means, in the case of fluidized bed, if you wanted to know what is the constant pressure drop, so only thing that you need to know what is the voidage, that is it. And because fluid density, particle density are known, rho s are known, rho s is the particle density and then rho E is the fluid density, those things are known, g is known, the height of the packing fluidized height is known. So, only thing that you need to know is epsilon. Once it is known, you can know what is that constant pressure drop. Okay. So, there may be some discrepancies obviously between the observed and calculated minimum fluidation velocities, because the same reasons are there for minus delta P versus V naught curves also. These are channeling, wall effects, agglomeration of small particles, and then interlocking of particles if the particles are having like needle like shape, etc. Then for streamline of flow of power law fluid through a fixed bed of spherical particles, relation between the liquid velocity, bed voidage and pressure drop we have already calculated in the previous lecture, and then that is given by this expression, right. So, in this expression, in place of minus delta P, if you substitute rho s minus rho L 1 minus epsilon g, then you can get whatever the velocity V naught at which the fluidation is taking place. So, here in this equation R e star, this is also we have derived in previous lectures. So, now equation number 6 is this one, and then 7 to 8, what does it mean by, now you are trying to find out V naught actually at the minimum fluidized conditions, or the flow is under streamline conditions, but still the fluidation is taking place. Then what is the velocity at which the fluidation is taking place, that you wanted to know. So, that you can get from this expression, because in this equation 7 delta P is known from this equation number 6, right. R e star is given by this one. So, now you substitute in place of delta minus delta P, you substitute this equation 6 here. In place of R e star, you substitute equation number 8 and then simplify, then you get V naught is this one. Simple rearrangement you can do it. So, this equation if you substitute n is equals to 1, you get this equation which is nothing but Koznik-Harman equation. Now, this equation we are doing when we are saying minus delta P is constant by this equation, that means it is under fluidized conditions, right. So, now in this equation if you substitute epsilon is equals to epsilon mf, what is epsilon mf? Epsilon mf is nothing but the voidage at the minimum fluidized conditions or incipient fluidization conditions, whatever the voidage of the bed is there, that we are calling epsilon mf, and it is the maximum voidage for the fixed bed condition. because after that condition, after that corresponding velocity, the bed is no longer going to be under fluid under a fixed bed condition, it is going to be under fluidized conditions. So, it is minimum for the fluidized bed condition. So, that minimum at minimum fluidized conditions, whatever the epsilon is there, that you substitute in this equation, then whatever this V naught is there, that we can call it minimum fluidization velocity. Okay. So, this is how we can get the minimum fluidization velocity, but it is only for the streamline flow of power law liquids. But always it is not possible that you have only streamline flow, then we have to have the contribution from the turbulent flow also. So, whatever plus 1.75 is required in equation number 7, that should be taken into the consideration. Then how these equations will change. So, minimum fluidization velocity at a point of incipient fluidization, bed voidage epsilon mf depends on shape and size range of particles, but it is equals to approximately 0.4 for isometric particles in general. Minimum fluidization velocity Vmf for a power law fluid in streamline flow can be obtained by substituting epsilon is equals to epsilon mf in the previous equation number 9 in the previous slide that we have seen. Although this equation applies only at low values of Reynolds number, this is not usually limitations at high apparent viscosities of most of the non-Newtonian fluids. We understand that apparent viscosity, although the viscosity changes for non-Newtonian fluids with respect to the shear rate and all that. So, but the apparent viscosity whatever is there, that is local value of shear stress divided by the shear rate whatever is there, that is apparent viscosity, that is usually very high for non-Newtonian fluids. So, then in general we whatever this limitation that we have seen, that is fine. Okay. So, at high velocities flow may not be under streamlined conditions, and more generalized equation must be used for pressure gradient in the bed. So, that is epsilon is equals to epsilon mf and V naught is equals to Vmf in friction factor equation whatever f is equals to 180 by R star plus 1.75 is there. So, there we have to substitute. So, when you take both the contributions from the streamline as well as the turbulent flow region. So, this is what we have this equation, right. So, now this equation here Fmf is related to minus delta P by L, right. So, minus delta P by L we know is rho s minus rho 1 minus epsilon g from the fluidized conditions. So, that we can substitute here, right. REMF is having Vmf. Fmf is also having Vmf values. So, solving these equations becomes very difficult. So, then what we have? We will have like this without Vmf value you cannot calculate Re star mf or Fmf star or Fmf as well, right. So, but we are doing all this analysis in order to calculate this what is Vmf. So, in order to avoid such kind of complications, what we do? We do some mathematical simplifications here, rearrangement of equation, something like that. So, what we do? A replacement of Fmf by Galileo number eliminates the unknown Vmf which appears in the Reynolds number. For that what we do? In the equation number previous equation number Fmf is equals to 150 by Re mf star plus 1.75, you are multiplying both sides by Re star mf whole power 2 by 2 minus n. Here Re star mf is same, definition is same as Re star that we have seen previous lecture for packed bed, only that wherever epsilon is there, epsilon should be replaced by mf, epsilon mf, and then V naught should be replaced by Vmf, that is the only difference. So, when you do this, whatever the left hand side f multiplied by Re mf star power 2 by 2 minus n is there. So, that we are calling it Galileo number, and then right hand side. So, this is the things that we have. Okay. So, Galileo number at minimum fluidized conditions GAMF is nothing but this one, and then FMF is nothing but this one, F rho s minus rho g d epsilon cube by rho V naught square. This is what we have seen in previous lecture, but epsilon is replaced by epsilon mf, and then V is replaced by Vmf for the case of mf, Fmf, right. Re star, this thing we know, right. So, Re star we have already seen in previous lecture, as well as the previous slide we have also seen. So, Re star expression whatever is there, in that Re star expression what you do, Re star by epsilon is equals to epsilon mf and V naught is equals to Vmf. If you do that, you substitute here and then simplify. So, then whatever this Vmf square is here, and then here also you will be getting Vmf square by after substituting Re mf star here, then that will be cancelled out, and then you will be getting Galileo number is like this. Now, here this Galileo number, there is no Vf requirement, unknown Vmf is not required here. In this Galileo number there is no unknown Vmf value, right. So, for a given fluid, that is Mn rho are known, particles rho s d epsilon mf also known for a given conditions. So, Re mf star you cannot obtain directly. Now, what you do, you Galileo number you first obtain, right. From this Galileo number what you do, you Galileo this whatever the Galileo number you get from this equation 13, because you only need the epsilon mf, particle properties and then fluid properties, all that you substitute. So, then you get the Galileo number. This Galileo number you substitute in equation number 12, then you find this Re mf star. Once Re mf star is known, so from there you can get Vmf. Okay. We see an example problem now. So, a bed consists of uniform glass spheres of size 3.57 mm diameter, density of particle is given this one. What will be the minimum fluidizing velocity in a polymer solution of density? Fluid density is given this one, rho is given this one, and then fluid is a power law fluid with these constants. Assume the bed void is 0.4 at incipient fluidization velocity. So, that means this is epsilon mf, not epsilon, it is epsilon mf is given. So, what you need to find out? You need to find out minimum fluidization velocity. So, in the problem it has not been mentioned whether the flow is under the streamline conditions or turbulent conditions, that it is not mentioned. And then we cannot find out as well, because in order to know whether the flow is under streamline conditions or not, we have to find out Vmf, that we do not know. Indeed, we are solving this problem to get that Vmf. So, for that reason what we are doing now, we first calculate the Galileo number. Okay. So, this is the equation that we have. Here in this equation Galileo number is given by this one. After substituting Re mf star and then simplifying, what we get Galileo number, we got this expression. Now, here in this equation when you substitute all these numbers, so then you get Galileo number is 83.2. This 83.2 you substitute here and then solve this equation for Re mf star. When you do that one, you get Re mf star is equals to 0.25, that is the flow under streamline conditions only. And then once Re mf star is known, then this is the Re mf star. So, then here everything is known except Vmf. So, then you can get the Vmf and then that comes out to be 2.36 mm per second. Straightforward, simple. Only thing this equations slightly difficult to solve directly. So, then you have to do trial and error approach. Okay. Now, before ending today's class, what we see a few details of dispersion in fluidized beds, and then we wind up the discussion on the flow through multiple particle system. So, discussion presented on dispersion in packed bed is also relevant to the fluidized beds in general, including that differential equation for the dispersion in packed beds and all that. But only one experimental study reported by these people. They have measured DL by introducing a fluorescence dye into beds of glass and of aluminum spheres. fluidized by CMC solutions of limited n values, and they found that whatever this correlation Pe is equals to 0.2 plus 0.011 Re1 power 0.48 is there, the same equation can be used with a slight modification where this Peclet number is multiplied by a parameter chi naught, that is chi naught Pe is equals to 0.2 plus 0.011 Re1 power 0.48 should be the equations for the dispersion in fluidized bed according to these people. What is this chi naught? It is ratio between V naught to Vmf to the power of 2 minus n. If it is 1, then obviously it is packed bed conditions. And then whatever this Re1 is there, that is based on the V naught, it is not based on the Vmf. Okay. Re1 definition whatever is there, it is based on the superficial velocity, not the minimum fluidation velocity. So, liquid solid mass transfer in fluidized beds, here also very limited studies are available. Kumar and Upadhyay measured rates of dissolution of spheres and cylindrical benzoic acid pellets in a fluidized bed by CMC solution of only n value 0.85. Then they measured the mass transfer coefficients on the basis of plug flow model from measured rate of weight loss of the particles using log mean value of concentration driving force at inlet and outlet of the bed. So, under such conditions they measured the mass transfer coefficients and they found whatever their packed bed correlation is there. So, this is the correlation they have developed for the packed bed, mass transfer in packed bed conditions. The same correlation may be used, same correlation may be used without any problem, but however this over predicts at low Re. Huang et al. Measured concentration with fluidized beds of cylindrical pellets of benzoic acid for a number of CMC solutions n is equals to 0.63 to 0.92, and then they measured longitudinal concentration profile by combining plug flow model with axial dispersion, and they found this equation whatever is there is they have used this equation to calculate dl together with experimentally determined concentration profiles, and then mass transfer coefficients were evaluated in terms of Re prime between 0.01 to 600 and Schmidt numbers varying, and they proposed this correlation. So, all these correlation Kumar and Upadhyay or Huang et al. Whatever are there. So, all these studies are experimental studies and then their experimental results are there, they are empirically correlated, and then these are the results. In this equation effective viscosity is required for defining the Reynolds number. So, they have used this expression, okay. And then Re prime they have used rho V naught d by mu effective 1 minus epsilon. Here also Re prime is defined based on the superficial velocity, not the minimum fluidation velocity, and then whatever Jm is there, that is given by Kc by V naught Schmidt power 2 by 3. References: the entire lecture is prepared from this excellent book by Chabra and Richardson, which is a very excellent book especially for non-Newtonian flow and applied rheology. Other reference books are provided here. Thank you.